Hello, guys. Welcome to the series of lessons in kinematics, science of motion. You know that kinematics started with brilliant works of the famous Italian scientist Galileo in 16th century. He is the father of mathematical physics. For the first time, he applied mathematics as a language to explain the concepts of motion. Nowadays, we still use the same language. So let's start with the concept of time and let's continue with the space. And then at the last part of this video, I will have a very introductory discussion about the motion. If you are ready, let's start with the concept of time. Time is a basic quantity. It's very hard to explain, very hard to understand, but let's accept it. For the time being, I'm not going to define the time for you. But time interval is very easy to understand. Suppose that I use a stopwatch, a clock, or any similar apparatus to measure the time. Mathematically, you can visualize the time using a number line. Suppose that it's the t-axis here. And let's say the time starts at t equals 0 based on something we read on the stopwatch. So negative time is meaningless for me. An event starts at t1 and ends at t2. Delta t will be the time interval. The last moment minus the first moment. Delta, mostly in physics, indicates change. For instance, suppose that delta t is 4 seconds. An event starts at t equals 8 and ends at t equals 12. So time interval is 4 seconds. What if the time interval gets smaller? It's not that big problem. Yeah, it could be smaller and smaller and smaller. But it may be too small not to be easily measured, out of the scope of any measurement. At that time, it's called instant. So what the instant is still a delta t, but a very small delta t which has no value. It's too small to be measured. So it's a relative concept. Based on that, we can say that delta t, which is approaching 0, is the instant. So instant has no value, it's a concept. When I say something happened in an instant, means that it was really, really fast. Something that we can't measure it. Anyway, it has had a duration, but the duration has been very small so that it's out of the measurement scope of the apparatus we use to measure the time. So a very, very, very short time interval is called instant. Now let's characterize the properties of a space using the Cartesian coordinate system x, y, and z. This coordinate system is a set of three different axes perpendicular to each other, and it was invented in 17th century by the famous mathematician, philosopher, and physicist Descartes. In this space, I can put a point like A, and I'm gonna give you the address of that point, where the point A is in this space. To address this point, I draw a vertical line first, parallel to z-axis. And let's say that the common point with this xy plane and this vertical line will be the point Q. Okay? From the point Q, I draw a couple of lines, one of them parallel to y-axis and the other parallel to x-axis. And let's name it M and the other N. From O to M, I have a distance which is called x1, the x component of the point A. Likewise, this is the y component of point A, y1. To find the z component of A, I draw the diameter of this rectangle from O to Q. And then I draw a parallel line to OQ. And let's say it's the point R. AR will show you a vertical distance from O to R, which is the z-axis of the point A. So a triple like x1, y1, and z1 will make the properties or the characteristics or components or coordinates of the point A in this space. This is a special address for the point A. But what the motion is? Suppose that A is an object and then it travels through a very complicated trajectory and gets the destination B. B is the destination with its own special set of coordinates x2, y2, and z2. What the trajectory is, trajectory or footprint or track, is the set of points through which the object travels. And what the motion is changing coordinates with time. That's all. Sometimes the motion is very complicated like that, which happens in 3D space. Sometimes it's very easy to consider. For instance, a train. Suppose that a train ideally goes through a straight line. And so this straight line, it could be, for instance, the x-axis. This is a very common example of the 1D motion, one-dimensional motion. The other could be a ship or a boat. If I forget about the curvature of the Earth, in a small region of the ocean, I think a boat can almost move on a plane, which is the two-dimensional space characterized by xy plane. But inevitably, an airplane is manifesting a very complicated three-dimensional motion. The easiest case of a study in kinematics will be one-dimensional motion. Let's say it's a toy car moving through a straight line from left to right, something like this. To characterize this motion, I can use the x-axis, mathematically characterizing the space. And moreover, when the car starts to go, I start measuring the time using a stopwatch at t equals 0. Rather than filming, I can make a photography every 1 second. So in the way, I have a few photographs every 1 second, as you see. At t equals 1 second, the car has been at x equals 4. So let's say it's 4 meters. It's arbitrarily taken as a unit. And also t equals 2, the car has been at x equals 8, and finally the car stops or ends the journey at t equals 3, x equals 12 meters. The positive direction of the x-axis is rightward in my coordinate system, and leftward will be the negative direction. It's arbitrarily taken. Moreover, you see that the car is displaced for 12 meters in delta t, the time interval of 3 seconds. This is a ladybird on a piece of paper. This insect can have this journey on this trajectory, which is not a straight line. So inevitably, you should use a coordinate system like yx to characterize the motion. The beginning point may have the coordinates of x equals 3 and y equals 4, and the final point x equals 28, y equals 13. You can have the same photography every 1 second, but it's not easy to explain the motion. You see, I know that delta t, the time interval of the motion, is 5 seconds. But if you ask me how many meters this insect has traveled, I can't say it's just the length of the footprint. It's also possible to connect the beginning and the last point with a line and define something different, which is displacement. Displacement. But the length of the footprint is called distance. Which one do you mean? Both are possible to explain and to measure. This is something which is added to the properties of motion inevitably when you go to two-dimensional motion. Of course, displacement and distance could be defined in one-dimensional motion, but they are very important and totally different and distinguished in two-dimensional and three-dimensional motion. Distance and displacement are the two important subtopics for the next video. So let's postpone it to the next video and consider all the details one by one to learn them. See you in the next video, and again, I'm very thankful for being with me. Take care and see you.